Now we will present some basic examples demonstrating the idea of Newton's third law of motion. In the second law of motion, the concept of the force acting on point-like bodies was introduced to describe the effect of other bodies on the given body. That is, by definition, only other bodies are able to exert a force on a given body in mechanics. For example, if we consider the rolling ball A, which changes the direction of its motion after the collision with the ball B, then we can state that the ball B has an effect on the ball A at the instance of their collision. By applying the point mass model, we can say that a force is exerted on the point mass A by the point mass B, which changed its state of motion. Then the question arises, what happens to the ball B when it exerts the force F on the ball A? We can find the answer if we examine some simple examples. In the original example with the colliding balls, we can see that ball B also changes its state of motion due to the collision. Either it changes the direction of its motion if it was already in motion, or it starts to move if it was at rest. But we can also examine a static situation. If we grasp a heavy table and pull it, then we feel the pull of the table with our hand. If we push it, then the table pushes against our hand. That is, we apply a force on the table, and at the same time we also feel the force exerted by the table. In this example, the body A represents the table, and the body B represents our body. Similarly, if we give a shot with a gun, then we feel its pushback with our shoulder by the recoil. That is, the gun exerts a force on the bullet as it is launching it forward. At the same time, the bullet also exerts a force on the gun and our shoulder, pushing them backward. In this example, the body A represents the bullet, and the body B represents the gun and our shoulder. Another trivial example is disembark. If we jump out of a boat to the river bank, then the boat moves away from the bank. That is, the boat exerts a force on us in the direction of the bank when we jump out of it, and at the same time we also exert a force on it in the direction of the water. In this example, the body A represents our body and the body B represents the boat. There are many more examples for this phenomenon, which demonstrate two things. First, if the body B exerts a force on the body A, then the body A also exerts a force on the body B in the opposite direction. Second, the greater the force that is applied on the body A by the body B, the greater the force that is produced by the body A. Now we consider an experiment which allows us to have some qualitative analysis of this phenomenon. Let us suppose that the persons A and B are standing on two seg scooters, with the opposite ends of a rope in their hands. We will study three different cases with this experiment setup. In the first case, the person A pulls the rope, whereas the person B just holds it. In the second case, we exchange the roles of the persons, the person B pulls the rope, while the person A only holds it. In the third case, both the persons pull the rope. If we perform this experiment, then it turns out that all the three cases have the same result. Both the scooters will move closer to each other, and if the masses of the persons plus the scooters are the same on the both sides, then they meet in the middle. This result indicates that the force produced by A and exerted on B, and the force produced by B and exerted on A have the same magnitude and in the opposite direction. Because of the friction of the wheels, the earth has some insignificant effect on the horizontal motion of the scooters. However, the experiment has a symmetric setup, and the amount of any frictional force produced on both sides during the motion is the same. As a result, we can assume that the conclusions drawn from this experiment are reliable. We also need to note that these results do not depend on the nature of the forces applied on the bodies, which is demonstrated in the following experiment. If we insert small magnet and iron bars with the same mass in two corks, and let them float on the water, we can study the effect they have on each other. If the corks are close enough so that the magnet has an effect on the iron bar, then they approach each other and travel the same distance until they meet. This result shows that the magnet bar attracts the iron bar just as much as the iron bar attracts the magnet bar in the corks. In other words, the force exerted on the iron bar by the magnet and the force exerted on the magnet by the iron bar have the same magnitude and in the opposite direction. In general, we can say that all experiments using forces of different nature have the same results related to the mutual action of two or more bodies. That is, mechanical forces, gravitational forces, elastic forces, magnetic forces, and so on can produce the same phenomena in nature, and we can generalize the conclusions drawn from the result of the experiments presented here. This generalization leads us to Newton's third law of motion, which is also known as the law of action and reaction. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. By applying the point mass model for the bodies A and B acting on each other, we can say the following. If a body B exerts a force FAB on body A, then A simultaneously exerts a force FBA on B, or in mathematical form, FAB is equal to minus FBA. According to this law, forces always appear in pairs, but these forces in the pair force, called action, and opposite force, called reaction, always act on different bodies. Newton's second law states that the force F acting on a body is equal to the mass of the body times its acceleration, which can be substituted in the mathematical form of the third law applied for the bodies A and B acting on each other. If ma is the mass of the point mass A, and aab is the acceleration of the point mass A produced by the force F in B, and similarly, mb is the mass of the point mass B, and aba is the acceleration of the point mass B produced by the force FBA, we can write that the mass ma times the acceleration aab is equal to minus the mass mb times the acceleration aba. This equation shows that even if the magnitude of the action and reaction is the same, the ratio of the magnitudes of the accelerations is determined by the ratio of the masses of the bodies. That is, the ratio of the magnitude of the acceleration AB to the magnitude of the acceleration ABA is equal to the ratio of the mass MB to the mass MA. Let us discuss the consequences of this formula. We can return to the experiment with the persons A and B standing on said scooters and pulling the two ends of a rope. If the total mass of the person A and the scooter he stands on is 2 times greater than the one of the person B and his scooter, then the acceleration of the person B is 2 times of the acceleration of the person A, as long as no other bodies have an effect on their motion. Another example in which the interacting bodies have enormously different masses is the free fall of a ball towards the Earth. When a ball of the mass m freely falls, it has the acceleration g, and by the virtue of the third law, the ball has also an effect on the Earth with the mass denoted with capital M. Then the Earth moves with the acceleration a given by the ratio of m to capital M, times g in the direction of the ball with respect to the inertial frame of the fixed stars in the sky. Since the ratio of the mass of the ball to the mass of the Earth is enormously small, this acceleration is essentially zero. That is, the effect of the falling ball is negligible on the Earth. Indeed, everyday experience shows that falling or accelerating objects near Earth's surface have a negligible effect on the Earth, since their masses are negligible compared to the mass of our planet. We can also consider the static case of the interaction between the ball and the Earth, when the ball is at rest on Earth's surface. In this case, we have to treat the ball and the Earth as elastic spheres. The gravitational force F1, considered as action, and the opposite force F2, considered as reaction, press these spheres against each other, which deforms the ball and the surface of the Earth. As a result, the ball exerts a deformation force F2' on the surface of the Earth, drawn at the center C of the Earth. Because of the principle of action and reaction, the Earth also exerts the force F1' on the ball, which is equal to minus F2'. Overall, the force F1 plus F1' is exerted on the ball, and the force F2 plus F2' acts on the Earth. Since both the ball and the Earth are at rest, at least with respect to each other, these forces must vanish. That is, F1 plus F1' is equal to 0, and F2 plus F2' is also equal to 0. As a result, the opposite force F1' of the deformation force is equal to minus the gravitational force F1, and the deformation force F2' is equal to minus the force F2, which is equal to the deformation force F1. We can also consider slightly more complicated examples to study the consequences of the principle of action and reaction. In the first example, a ball is at rest either on a table or a spring, where we neglect the weight of the table or the spring. Based on the previous example, we know that the gravitational force F1 acts on the ball and its opposite force A, the force F2. These forces press the ball and the Earth together, and the ball exerts the deformation force F2' on the surface of the Earth via the table or the spring. As a result, the Earth also exerts the force F1' on the ball. At the same time, there are two other forces acting on the table or the spring transmitting the forces between the ball and the Earth. The force F3 is the weight of the ball, which is equal to the gravitational force F1, and the force F3' exerted by the Earth, which is equal to minus F1. These forces press the table or the spring which remains at rest. We draw the forces F2' and F3' along the axis of the spring. When the ball is at rest on the table, these forces are the vector sum of the forces acting along the legs of the table. Here we can see 3 pairs of action and reaction. The first force pair, denoted by A, is the interaction between the ball and the table or the spring. The second pair of forces is denoted by B, and it is the interaction between the table or the spring and the Earth. The third force pair denoted by C is the interaction between the ball and the Earth, which is transmitted by the force pairs A and B. In the next example, we suspend the ball through a string or a spring attached to a stand, where we neglect the mass of the string or the spring and we treat the stand as the part of the earth. In this case there are two forces acting on the ball. The weight F of the ball and the force minus F exerted by the string or the spring. The forces acting on the string or the spring are the following. The opposite force F exerted by the ball at the lower end of the string or the spring, and the force minus F exerted by the stand at its upper end. The force acting on the stand is the opposite force acting at the upper end of the string or the spring, which is just the weight F of the ball. This force transmits the weight of the ball to the earth, and this weight has the opposite force minus F. In this example, we also have three force pairs. The force pair A is the interaction between the ball and the string or spring. The force pair B is the interaction between the string or spring and the stand or the earth. The force pair C is the interaction between the ball and the stand or the earth, which is transmitted by the force pairs A and B. Based on these examples, we can state that a string with a negligible mass under tension can transmit a force acting on its one end to any object connected to its other end, without modifying the force. Then, in the experiment with the persons on scooters pulling a rope, we can regard the force exerted by one of the persons on one of ends of the rope, as a force acting on the other person holding the other end of the rope. We can conclude that the forces keeping a string or a rope under tension, or expanding and contracting a spring, act on both ends of them, and the forces have the same magnitude in the opposite direction. This conclusion can be demonstrated in the following experiment, where one end of a spring balance is connected to the wall, and a body is suspended from its other end through a string passing over a fixed pulley. And in another experiment, where two bodies with the same weight are suspended from both the ends of a spring balance. In the first case, the suspended body has the weight F1, and the force F1 pulls the spring balance. The force F2 exerted by the wall pulls the other end of the spring balance. In the second case, the suspended bodies have the weights F1 and F2, and the forces F1 and F2 pull the spring balance from both ends. The spring balance measures the force F2 in both cases.